Lesson 7. Principal stresses and Mohr's circle. At any point, a plane stress state has a normal stress in X, a normal stress in Y, and a shear. Rotate that element, and those numbers change. The principal stresses are the largest and smallest normal stresses you can find on planes where the shear vanishes. 3 one-line ideas. The principal stresses come from one transformation formula. Mohr's circle is that formula drawn as a circle with a center and a radius, and the radius is the maximum in-plane shear. Get those, and any plane stress point is a plug-in. Here's the problem. 1 point, 3 numbers, 80 in X, 20 in Y, and a 30 shear. Find the center of the circle, its radius, the 2 principal stresses, the maximum in-plane shear, and the angle to the principal plane. It's one formula drawn as a circle. Build it from a center and a radius, then read the answers straight off. Concept 1. The stress state rotates with the element. 3 numbers on the reference faces set the point, and spinning the element changes all 3. But 2 things stay fixed: the average normal stress and the overall size of the state. At one special angle, the shear vanishes, and those faces carry the principal stresses, the largest and smallest normal stress at the point. That special orientation is exactly what the exam is after. Concept 2. One formula gives both principal stresses. The average of the 2 normal stresses, plus or minus a radical. The average is the middle of the state. The radical is how far the state swings above and below it. Plus the radical is the maximum principal stress. Minus the radical is the minimum. One expression, both answers. Concept 3. That formula is literally a circle. Plot normal stress across, shear up, and the state sweeps a circle. Its center sits at the average normal stress. Its radius is the radical from the principal stress formula. Where the circle crosses the axis, you read the 2 principal stresses. The top of the circle is the maximum in-plane shear, which is just the radius. Center plus or minus radius for the normals, radius for the shear. Setup. Drop the 3 given stresses into the table. Then leave blanks for the center, the radius, and the angle. Only 2 real computations sit underneath everything: the center and the radius. Get those 2, and the principal stresses, the shear, and the angle all drop straight out. Solve. Part 1. Build the circle. The center is the average of the 2 normal stresses. The radius is the radical. The half difference of the normals and the shear are the 2 legs, and the radius is their hypotenuse. Here both legs are equal, so the radius is √2 times 30. Center at 50, radius about 42. The circle is now completely fixed. Solve. Part 2. Read the answers off the circle. The principal stresses are the center plus and minus the radius, about 92 and about 8, both positive, so the point is in tension on both principal planes. The maximum in-plane shear is simply the radius, about 42. Notice you compute nothing new here. It's all center plus or minus radius. Solve. Part 3. The orientation. The tangent of twice the angle is 2 times the shear over the difference of the normal stresses. Here that ratio is 1, so twice the angle is 45 degrees, and the physical principal plane angle is half of that, 22.5 degrees from the reference faces. The circle always speaks in double angles, so have it to get the real plane. Final answers: center 50, radius 42, principal stresses 92 and 8, maximum in-plane shear 42, and a principal plane angle of 22.5 degrees. One circle delivered every number. And a fast check: the 2 principal stresses add back to 100, exactly the sum of the original normal stresses. That sum never changes when you rotate. Traps. 3 ways Mohr's circle bites. 1. It works in double angles. The tangent gives twice the plane angle, so always have it. Reporting 45 instead of 22.5 is the number 1 miss. 2. Mind the sign of the shear. It decides which way the element plots and which way the plane turns, though the center, radius, and principal stresses don't care. 3. The maximum in-plane shear is the radius, the half difference of the principal stresses, at 45 degrees on the circle, not their full difference, and not half of sigma 1. Quick recall. The center is the average normal stress. The radius is the radical from the 2 legs. the half difference of the normals and the shear. The principal stresses are the center plus and minus the radius. The maximum in-plane shear is the radius. And the angle? The tangent of twice the plane angle is 2 times the shear over the difference of the normals. Build the center and radius, read center plus or minus radius, then have the circle's angle. Next up, Lesson 8, Combined Loading. We can now take any plane stress point and read its extremes off one circle, the principal stresses and the maximum in-plane shear. Next, we go one step upstream and build that stress state, superposing axial, bending, torsion, and shear on a single member to get the very inputs Mohr's circle needs. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.